Hello, everyone. How's it going? Hello. Is everyone doing okay? We're all ready to classify some particles. All of them. Hey, how's it going? Is this a first time for anyone? Or are we all seasoned professionals ready to take another swing? Yeah, there was, I think a lot of people really do like the particle stuff. I also think it's, the questions are quite fun on it compared to a lot of stuff because it's kind of, there's a difference between like problem solving and calculating, and it's kind of fun. You just have some weird symbols and you have to do some kind of, often it's like a process of elimination, like answering multiple choice type of a question. So that's quite cool. I know. I mean, wait, what am I saying? My job is to say that the most fun bit of physics is all of it. So I said nothing. That's all you heard, right? Okay. I'll just get us up, partly because I'm really excited to share this happy little one with you. Hello. Or hello. Yeah, I suspect we probably will actually, yeah. Not too many questions today. Lots of fun stuff to chat about though. Have people kind of seen stuff about particle physics, particles, antiparticles before? Is it anyone's first time? Yes, cricket crazy. I seem to remember. Yeah. So I know you've definitely seen some particle stuff. Well, pressure's on. Do people agree with this? Is particle physics the most fun bit of physics? Ah, hey, ladybirds. Ah, thank you. Ah, damn. Thank you. I'm glad it was your first ever circular motion class. So, yeah, I'm really happy with how that went. Yeah, I got you. Mechanics is not for you. Ah, but you do like mechanics. Mechanics often suits people who do, who like, well, partly if you're doing A-level maths, it's good because often you get a crossover. That's nice. No, circular motion is year 12. It's like bonus mechanics fun time for people who are fed up of making progress and just want to go round and round in circles. It's actually quite a cool topic. Circular motion is a surprisingly weird thing to think about. Yeah, it's usually a 13 topic. In fact, I think it is for every exam board at the moment, which is good because you need to know the earlier mechanics first to really understand it. Okay, should we get going? Let's have a crack at this. So today we're going to be learning to classify various particles, the zoo of particles and antiparticles that exist in the standard model of particle physics. Okay, so as always, just to mention, if you've been to these sessions before, there will be a coupon at the end of this that will give you a discount for SnapRevise. So if you're interested in that, I thoroughly recommend. It would be an absolutely banging thing to be interested in. I thoroughly recommend sticking around to the end so you can have a crack at it a month at a cheaper price and see what you think. Yeah, it's further mechanics, exactly right. Hello, Bob Lob. Cool. Excellent examinations. Yeah, year 13. Cool. Okay, so let's just slam straight in and chat about some questions. I'm just going to kind of use some exam questions as a jumping off point to see where we get to. So, state the mass and charge of an antiproton. So, is anyone able to do this? Wow, okay, we are slamming in with the answers. Okay, and how do you know that this is the mass of an antiproton? What's the statement about particles and antiparticles that you're using here? Because I don't know if your formula book said what the mass specifically of an antiproton was. So, good. And how do we find this? Well, any antiparticle has the same, any particle and antiparticle, let's say it like this, any particle and antiparticle have the same mass but opposite charge. So this is the key definition that we're going to be using to figure out this question. Same size and magnitude. Good. Okay, fantastic. So it has the same mass as a proton, which you can find in your formula book. 1.67 times 10 to the power minus 27 kilograms. Yeah, sure. So this is, we're going through classifying particles. So we're looking at some exam questions on particle physics. And we've been asked to state the mass and charge of an antiproton. So if you haven't seen the particle physics stuff before, what I would say is this. Antiproton means the antiparticle of the proton. And what's an antiparticle? Well, we've given the definition here. The antiparticle is the particle that has the same mass but opposite charge. We are indeed going to look at some hadrons and baryons. Exactly right. Good. Okay. So what about the charge? Well, the charge should be opposite to the charge of a proton. The charge of a proton is 1.6 times 10 to the minus 19 coulombs, the same as the charge of an electron. All ties together. However, it should have the opposite charge, so it should be a minus sign here. Liking having a hype man. Okay. Now, determine the quark structure of an antiproton. So here we're going to use another rule about particles and antiparticles. So, first of all, can anyone tell me the quark structure of a proton? So I'm not ill. I just have really bad hay fever at the moment. Sorry about all the sniffing. I will sneeze at some point, and it will be, what's the word? Catastrophic? Something bigger than that. Bigger than catastrophic. Good. Okay, so a proton. So yeah, watch out for the sneeze. Okay, so proton has quark structure up, up, down. The antiproton. So in an antiproton, you should switch all of its constituent parts to their antiparticles. So to go to an antiproton, so if this is given the symbol P, that would be a nice way to write this. To go from a proton to an antiproton, which is written with a bar, anti is the bar bit, then we just anti every particle that makes it up. So you're absolutely right. The antiproton is equal to the anti-up with the anti-down. Fantastic stuff. Okay. Yeah, so thanks so much for asking. I don't have like a cold or anything. I just really bad hay fever. Good. Actually, right, yeah, that's a nice thing to point out. What's the charge? Just so you know, the charge of an up quark is 2/3. The charge of an up quark is 2/3. The charge of a down quark is -1/3. If you add all these together, you get a charge of +1, which is the charge of a proton. Good. Okay, let's have a crack at another question then. So I think this is quite a fun one. From the following list of particles, identify all the examples of hadrons, leptons, antiparticles, and charged particles. Anyone who's able to smash through this, maybe you can also define for me the difference between a hadron and a lepton, so everyone can see it. Aha. So, Cricket Crazy. Not all quarks have a charge of +1/3. All quarks have a baryon number of +1/3. Good. Okay, a hadron is something that feels the strong force. What's the strong force? It's the thing that hadrons feel. Don't worry about it. But hadron is a thing that feels a strong force. Absolutely right. Leptons are things that don't. Hadrons consist of mesons and baryons. Oh no. If you haven't seen it before, it's yeah, I mean, going through exam questions is probably a hard way to learn things for the first time. So don't be too off put if this is too hard. Usually, you know, you'd have to have had some lessons or read the book a bit, and then you do some exam questions. No, I'm liking what Ahmed's saying. This is way more motivating. Yeah, stick with it, stick with it. Okay, so what are the examples here? Can anyone tell me which ones are which here? Which ones are charged? Maybe that's a good start. No, okay, let's go over hadrons first. Which ones are hadrons? I confused things now by asking about charged. So just, what's a hadron? So hadrons are things that feel the strong force. They're non-leptons. The ones that we're looking at here, well, hadrons include baryons and mesons. Someone told me this, and that's really useful here. Include baryons and mesons. Is there any baryons? Proton, yeah. What else? Antineutron, yeah, that's a baryon. What else? P and N, good. And there's one more. The other one we want is this pi naught. So this pi naught is called the pi naught meson. This is a meson. It's made of a quark and an antiquark. And it's absolutely a hadron. Good. This neutral pion is also a hadron. Well done. Okay, what about leptons then? So leptons will be, well, the good thing here is if you know the hadrons, all the leptons are the things that are not hadrons. All the hadrons are the things that are not leptons. So what are the leptons here? Good, electron neutrino, nice. The positron, good. So this thing here, for anyone who's wondering, is a positron. It's like a positively charged electron. Leptons are indeed fundamental. The muon. Okay, what's a muon? For anyone who's seeing this stuff for the first time, a muon with its negative charge there is just like a really heavy electron. Basically behaves in the same way other than being way heavier. Heavy electrons, absolutely right. Yeah, good question. Okay, so just like I said, the anti-neutron was a baryon. Baryons, okay, so baryons are things that feel the strong force. The things that feel the strong force are typically these things that are made up of quarks and so on. The leptons are the things that don't. And I can tell you right now, if an electron doesn't feel the strong force, then its antiparticle, which should behave almost exactly in the same way, also shouldn't feel it. So the definition is there's no such thing as the category anti-leptons. Leptons are just things that don't feel the strong force, and they include particles and their antiparticles. Good, okay. So which particles here are antiparticles as opposed to normal particles? So one of them, there's a hint because antiparticle we always represent by putting a bar on top. So there's the anti-neutron, good, which is this one. The other one is more subtle. The electron, so an electron is a fundamental particle, a normal one. And this thing here, the positron, it's a positively charged electron. And that's a hint because antiparticles are the things that have the same mass but opposite charge. The positron has opposite charge to an electron. Positron. Since the electron is a normal particle, the positron must be an antiparticle. Finally, which particles here are charged? VE is what's called an electron neutrino. So if you haven't studied particle physics at school yet, you might not have come across this. The electron neutrino is this kind of ghostly particle that just exists to kind of conserve momentum in different particle interactions, along with some other numbers actually that should be conserved. Positron. Good. Okay, so here the charged particles are the positron. Good. The proton. Good. And what else? The muon. Fantastic. How do I know this one isn't charged? The pion. What was my clue? Yeah, there's 0. So for mesons, you typically draw a little symbol up here that says what the charge is. Absolutely right, good. So this is the neutral pion. There are also charged pions, which we write like pi plus or pi minus. Fantastic. Good, well done, everyone. So let's look at another question. The omega minus particle. So now things are getting crazy. Okay, the omega minus particle is a baryon with strangeness -3. Whatever strangeness is, it must be even stranger to have -3 lots of it. It rapidly decays in stages to a baryon and several pions. Okay, these are things we recognize a bit more. State the general quark structure of a baryon. So if people haven't seen particle physics before, this is a good time to, you'll get to learn this bit now. Good. Okay, the general quark structure for a baryon is it's either made of 3 quarks. Now, for anyone who's seeing this for the first time and is wondering what quarks are, I will say they are these small fundamental particles that the things called baryons are made of. It just turns out you can go one step lower than like protons and neutrons, and they're made of little things called quarks, and they typically have labels like up, down, and strange. Okay, so 3 quarks, 3 anti-quarks. 3 quarks or 3 anti-quarks. Good. Okay. State what class of particle a pion is. Give its general quark structure. Are quarks smaller than electrons? Couldn't say off the top of my head. I think they're both treated as being point-like. So they're both kind of unimaginably small. Maybe quarks have a size, I'm not sure. You won't need to worry. Although I wish I knew. I wish I knew. Maybe I'll come back to you if you have time at the end. I think because they said general quark structure here, you really, to say that baryons are always made of 3 quarks is just not quite true. So I think you want to say quarks or antiquarks. Good. Okay. Good. So the pion is the other type of hadron. So remember there was 2 types of hadrons. Baryons and mesons. And you're absolutely right. A pion is a meson. It's the other type of hadron. Now, what's the general quark structure of a meson? Do we know? So I don't have the exact mark scheme in front of me right now, but my opinion is yes, you would need to give both here. Good. Okay. A quark and an anti-quark. In fact, yes, you really would need to give both there. Good. Okay. A quark and an anti-quark. And anti-quark. So some classic examples of baryons would be things like the proton, which is up, up, down quarks. The neutron, which is up, down, down quarks. And here, well, there's all sorts of options. Any 2 quarks you want to put together, one normal and one anti. So up, down bar, up bar, down, strange up bar, you name it, it's a meson. Good, okay. State which pion is identical to its antiparticle. Pi naught. Okay, why did you choose pi naught? It's correct. Yeah. So yeah, we can mention this. So first of all, what pion is identical to its antiparticle? Absolutely right. So the antiparticle is the thing that has opposite charge to the particle. So it's probably going to be the neutral one because the opposite of neutral charge, the opposite of a 0 charge is still 0. So we'll state it first. The neutral pion is the thing that's equal to its antiparticle. Another way of seeing this is that the neutral pion is made of a pair like this. It's like a down or down with an anti-down, or it can even be something like an up with an anti-up. Now, what happens when I make the antiparticle out of this? Well, I switch the D to an anti-D. I switch the anti-D to a D. And look, I've still got an anti-D and a D. It's the same particle I had before. So the pion really is, when you try and take the antiparticle of a pion by looking at the bits it's made of, you still get a pion. Really nice. Good stuff. Okay. So let's have a go at another question. The table below shows some quarks and their properties. A pion, so let's start with question 8 here. We're asked to pick an answer. A pion could consist of A, up down bar, B, up down, C, up down, D, up down bar. One of these is correct. Which one is it? Absolutely right. Why are we choosing A? Well done. So the reason for A is a pion is a meson. And a meson is a quark anti-quark pair. We said here, yeah, the general structure of a pion is meson, and mesons in general are a quark and an anti-quark together. So only one of these presents just an anti-quark and a quark together. It's this here, up with anti-down. Absolutely right. Well done. Good stuff. Okay, so table C then. Some quarks and their properties. And we've even gone further than strange now. We've got a new quark called charm. In part I, we're asked to circle the correct combination of quarks in the list below, which corresponds to a D0 meson. Now, I'm going to give you a hint here. I don't know, without looking at the answer, what a D0 meson is actually made of. So we have to find a way to figure this out from the table. What 2 facts do we know about the D0 meson? Okay, I see some people are already smashing to the answer. So let's see. Good, there's 2 facts here, and we want to make use of both of the facts. This is essentially a process of elimination a question. Meson, what does that mean? It's a quark and an anti-quark pair. So that gets rid of this. There's no way it can be this because that's 3 quarks. Can't be this because that's 3 quarks. Okay, so it's one of these 2. What other piece of information do we have? And I think, yeah, never drink and derive, you pointed this out. It's got a neutral charge. So also charge, because of this 0 here, charge should be equal to 0. So let's figure out the charge of each of these. What's the charge of C anti-up? And you're absolutely right. The charge of C anti-up is 2/3. And then, well, okay. So an up is 2/3. So what's an anti-up? Minus 2/3. And we see indeed for C anti-S, we would have 2/3. And then the anti-strange would be plus 1/3. That would be equal to 1. Yeah, okay, so it can't be this because it's got to be neutral. So you're absolutely right. Some people are able to smash straight into that answer. Yeah, it's good, isn't it? C and anti makes a 0 charge. Good, well done. That was really good stuff. Really well done. Okay, next question. A particle called a B meson has been observed to decay into an antiproton plus a lambda particle. That bracket there is just like capital lambda. Okay, The lambda particle consisted of an up, a down, and a charmed quark. Let's write that down because they haven't said it. Okay. Up, up, down, charmed. Okay. The following table summarizes the charges on these quarks. Circle the correct word from the list below to describe the lambda particle. Good, okay. And why are people saying baryon? Why are people screaming baryon from the rooftops? Good, it's made of 3 quarks. It's got a baryon number of 1. That's a nice way to think about it. Baryons are the things which consist of either 3 quarks or 3 antiquarks. This consists of 3 quarks. Whoa, where are we? Yeah, here. Up, down, charmed quark. Up, down, charmed. Good. Okay. So you're absolutely right. The answer is baryon. It's made of 3 quarks. Finally, we are asked to calculate the charge on the lambda particle. Okay, how can we do this? No, it cannot. Good, really good question. It's either 3 quarks or 3 antiquarks. No other option. Okay, if we want to calculate the charge on the lambda particle, we're going to want to go to this table. It's made of an up quark, a down quark, and a charmed quark. So we just add these charges together. We get 2/3 minus 1/3 plus 2/3. Well, what's that all together? That's equal to 1. Good. Okay, so the charge on the lambda particle is equal to 2/3 minus 1/3 plus 2/3, which is equal to 1. Well done. Okay, let's jot that there. Write an equation using standard particle symbols for this decay. Okay, it's kind of a funny question. No, I don't have a drop-in today. My next drop-ins are Monday and Wednesday, 12. Yeah, the baryon number was 1. Okay, so this last question, write an equation using standard particle symbols for this decay. Well, what's the decay? Let's go back and see this. So the B meson, so just something called B, decays into an antiproton. I won't give you the symbol yet because I'm going to want the symbol from you. Antiproton plus lambda. So B meson goes to antiproton plus lambda particle. Okay, so we have to have a little think about what's going on here. This B meson. Well, so let's just start off by writing the symbols. We use a letter B for the B meson. What do we know it goes into? We know it goes into an antiproton. So how do I draw an antiproton? An antiproton is a proton with a bar on it. So really what they're asking for us to do is to take the sentence that they wrote about particle decay and just write it as an equation, which really just means making the right symbols and putting an arrow between them. So there's an antiproton here. And finally, there was this lambda particle, which again, we'll just represent with the symbol lambda. Now, we do have one thing we need to do, which is for any meson, because this doesn't feel like 2 marks worth of an answer. We just wrote down what they said. P with a bar on top. Good, yeah, okay. Now, when we have a meson, do you remember when I drew the neutral pi? We drew a little symbol up here. So for any meson, we need to express what the charge is up here. So that's the one thing that we haven't done yet. We need to figure out the charge of this particle here. So what is the charge of this B particle? Does anyone have any ideas? The hint is to know that the charge should be the same on the left and the right hand side. Okay, so the charge here should be the same as the total charge here. The charge before the interaction should be the same as the charge after. Now, the charge of an antiproton is -1. The charge of the lambda particle was +1. So what should the charge of the meson be? Good, yeah, I'm seeing some really nice answers here. Good. 0. This adds up to 0 here. So this should also be 0. And that means the last thing we need to do to finish this equation is to write a little symbol here that expresses that we have a neutral meson. It's kind of a slippery question, that bit. So it's, yeah, I think it's cool to have seen. Good. Yeah, exactly. This is the law of conservation of charge. There are 2 other conservation laws as well. Conservation, well, there's loads. Conservation of energy, conservation of mass, but the other 2 kind of fancy ones that come up in particle physics are conservation of baryon number and conservation. Yes, strangeness is a slippery one. It's often conserved. But in terms of the ones that are always conserved, baryon, charge, and lepton. Those are the key ones. Those are the ones you want. But sometimes mass number is helpful too. Energy you can't really see in these equations. So energy is often a little less helpful. Okay, fantastic. Really well done. That was really good stuff. No, so that's the end of the session today. I mean, we've spoken a little bit about conservation in the end because we had to figure it out to correctly symbol up this. Aha, yeah, no, not a gamma ray, a big old baryon. In the world of particle physics, actually a relatively heavy particle, especially because the charm and strange things are even heavier than normal quarks. Okay, fantastic. So that was really cool stuff. I very much enjoyed that. I'm just gonna, for anyone who hasn't kind of seen this before or would like to see again, I'm going to do a little SnapRevise walkthrough to kind of show you what we do on the site. In particular, there's a quiz on there about hadrons and leptons that I thought would be really appropriate. So we can have a quick smash through that and see what SnapRevise tells us we ought to do with our answers. So I'm just going to show you a little quiz. Let's get this up. I think this is going to be fun. Okay, so I'm just going to log into my favorite account of all, Success. I'm now in my SnapRevise account. Perfect. Okay. So thanks very much everyone for coming. Well, let's have a look at a little quiz. So if we go into year 12, there's some questions here we could look at. Quarks, baryons, and mesons. We didn't get as far as conservation laws, so let's look at quarks, baryons, and mesons. Okay, so we're going to start what's called a diagnostic quiz. And this is great. The idea is we have a go at this quiz, and based on the things that we get right and wrong, there's a smart adaptive learning system here, so it will tell us what videos we need to go and watch to get back up to scratch and what ones we don't need to, that we could just watch for fun. Okay, so let's absolutely not skip the quiz. Let's have a look and see what we know. Which of the following is the most accurate definition of hadrons in terms of quarks? What do we reckon? Hadrons are particles made up of 3 quarks. Hadrons are particles made up of a quark and an antiquark. Hadrons are particles. Wow. So usually it's thing that feels a strong force. In terms of, we know that hadrons are kind of mesons and baryons though. So it's probably just the stuff that's made of quarks and antiquarks. Okay. A hadron with charge 0 is made of a strange quark and an unknown quark. What is the unknown quark? Wow, okay, these are quite hard. Let's see. It's made of a strange quark and an unknown quark. What is the unknown quark? Well, a strange has a charge of, well, -1/3. So yeah, it's going to be strange, anti-strange. Oh, sorry, anti-strange. Yeah, strange, not strange, anti-strange. Well, this is good. Now I got one wrong. Trying to go too quickly. Okay, what is the strangeness of a hadron consisting of 2 strange quarks and 1 up quark? So we didn't talk about strangeness yet. This is either going to be -2 or +2. It's -2. There you go. Okay, so now we're just going to smash through a couple to see what we just to get to the end of the quiz. What is the quark configuration of the antiproton? Yeah, we looked at this today. Good stuff. Charm, blah, blah, blah. We're not going to try this one. We're just going to smash through. As you can see, there's a good range of questions in terms of whether they're kind of figuring out constructions of things or whether they're definitions. Greater mass than a proton, not always true. Okay, now we're just going to smash through. See what we get right. Nothing so far. Okay, so here's my result. Tells me the stuff I knew. I got introduction to quarks, strangeness and baryons, smash through that. But what I don't know, what I need to work on is charges of quarks, baryons, mesons, chaos, so on. Now, it doesn't just stop here. That would be useful in of itself. But now inside SnapRevise, this is where stuff gets really cool. It loads me straight into all of the instructor videos, which are complete for each exam syllabus. And at the bottom of each video here, first of all, the videos which I need to be looking at are highlighted in orange here on the left. These are the ones that have bits that I got wrong in the quiz. So great, I can streamline my learning directly to the stuff that I was uncomfortable with in the quiz. As you can see, it's possible to ask questions and give comments at the bottom. Also, it's possible to skip straight to the bit that you struggled with. As you can see, this video now knows already, it knows that for me personally, introduction to quarks is green. I don't have to see this. See if I want, but I don't have to. I could click straight on the orange bit and go straight to the bit that I was struggling with, the charge of quarks. And here we get taken through and we'll have all the bits that we didn't understand explained to us. So this is a fantastic feature. Really the key here is to try and kind of streamline your learning to just the stuff that you still don't know that you really want to need. This is fantastic. We have revision guides that we set up. There are also our own kind of homebrewed exam questions for you to work through, including exam work through videos. So there's exam questions to look through, but also we've recorded videos of us kind of showing you how to answer various exam questions as well. So this is fantastic stuff. I'll just drop this stuff at the bottom here. Thank you so much for sticking with me. Okay. So we'll just have a quick look at the plan so that you can see what we offer. And as I said, I will give you the discount code in just a second. So there's 3 plans here. There's basic that gives you access to the teaching videos. So you can learn all of the stuff that we've been producing. We've been producing videos that are exam board specific that we really want you to watch because we really think they're great. Well, we know they're great. So, and again, we have the exam walkthrough videos and some mini revision guides for you. On the pro scheme, we have all of that good stuff that we had in the basic scheme, plus this smart adaptive learning system to try and help you streamline your learning. Not only this, we also have some predicted exam packs and some self-marking quizzes. And finally, there's the ultimate. So if you really enjoy this kind of tutoring experience that we're trying to kind of make more affordable, this kind of face-to-face learning and going through questions and being able to discuss. I mean, a typical tutor can cost upwards of, £50 an hour, which is kind of just a completely, just really difficult cost for most people. So our idea is to try and make a version of tutoring that's a little more affordable, a lot more affordable, in fact. So rather than for £50 for a session, our idea is, well, let's offer kind of some of the advantages of having a tutor like myself on board to help you answer your questions. So I run drop-in sessions on the website where people can just come in and ask questions that they want to go through, things that they're stuck on. I also run sessions where we go through specific bits of content and we talk through them together. And we do this, we figure, well, £50 for a session for a tutor, let's try and stretch that to £50 for a month. So that's our model. And we're very proud of what we've achieved so far. And yeah, I'd love to see some of you there. So thanks very much for sticking around and coming to the session. This has been really fun for me. I'll just bring us back up to the discount code so that we can see that. And if anyone's got any questions, just let me know. Yeah, so here are all of the upcoming study clubs. Yeah, keep a lookout for this stuff. We're doing all sorts of study clubs at the moment. And here is the discount code. So yeah, thanks very much for coming. Yeah, see you later. Let me know if anyone has any questions. That's really good fun. And that was a really good session today as well. Like, really nice and interactive. People very keen to answer and offer their 2 cents. That's what we love. Bye. Thanks very much. Bye. Cheers. I'll tell you what I found the hardest. That might not be the same thing. What did I find hardest? Yeah. I found thermal stuff hard. I knew the sneeze would come. Yeah, I found thermal the hardest. Just because it was kind of, oh no, I'm going to sneeze again. Sorry. It's hay fever, man. For a lot of people, I think further mechanics is quite hard. You have to do a lot of long calculations. I think that today was probably quite scary if you hadn't seen particle physics before. It's the hardest one to get into at the start because there's all these weird words, but I think it actually becomes the easiest one once you're used to the words. So that's nice. I don't know, what do you think is the hardest topic? A lot of the circuit stuff is kind of tricky. Because of the circuit stuff, you're given some fairly basic rules, but you get given some quite difficult problems to solve with them. So maybe that. Oh, actually, stress and strain stuff. I always struggled with stress and strain stuff. It's just, I don't know why, it just never kind of clicked for me. But yeah, I think electricity is the hardest in terms of problem solving. You get some really hard problems to solve there. Oh, okay. Well, if no one else has got any other questions, I think we'll leave it there. I look forward to seeing you all at the on our next study club. Great. Thanks very much, everyone. Great to see you all again, and great to see some new faces as well. Okay. See you later. Bye.